How the mystery of Herculaneum was solved with Raman spectroscopy. Almost 2,000 years ago, Mount Vesuvius erupted, releasing plumes of hot gas and ash, destroying the ancient city of Pompeii in its wake. The inhabitants of nearby Herculaneum were frozen in time, with the mystery of their death only being uncovered in recent years, thanks to the work of Dr. Pierre Petrone and his colleagues in Naples. Archaeological investigations on these skeletons uncovered dark red and black deposits inside the shattered skulls of the victims, leading to investigations into their origin, which helped uncover the harrowing fate of those frozen in time.
Raman spectroscopy is a chemical analysis technique that uses scattering of visible light. It's useful in many big cases because it requires minimal sample preparation and it's non-destructive. In a typical experimental setup, you have high-intensity single-coloured light shining onto the solid sample you're investigating. The atomic bonds that hold a molecule together are a lot like springs, and just like springs, they're able to vibrate. What Raman does is it allows you to investigate what frequencies a given sample vibrates at. This is interesting because the ways that different molecules vibrate are generally unique enough that the vibrational spectra acts like a fingerprint, allowing you to identify their presence in your sample. Once a photon of light enters your sample, it will begin to randomly scatter off many different molecules inside. Occasionally when that photon scatters, it exchanges some energy, which is transferred to vibrational energy within a molecule. Due to the energy change, the photon scatters away with a different colour. This is what's known as the Raman effect. Importantly, the amount of energy transferred is dependent on the frequency of the vibration the photon has excited, and in a given molecule, only certain vibrational frequencies are allowed. Some light that is scattered will eventually leave the sample to be collected together and measured. Your Raman spectra is just the intensity of each colour of light that is present in this scattered light. You then compare your spectra to a database of known materials and look for matching intensity peaks.
Join us at the University College London Nanotechnology Lab, where we will be showing you a Raman spectrometer in action. This is our Raman spectrometer at UCL. First of all, we open the machine, which reveals the microscope setup inside the chamber. This chamber is important to protect us when the laser is turned on. We now load the sample onto the sample stage and bring the sample into focus. Any sample you want to analyse must be removed from the bulk and a small piece is selected. Bringing the sample into focus allows you to analyse specific parts of the sample. The laser is then turned on and the Raman spectrometer gets to work. Once we select the run option, the laser will hit the sample, where the sample interacts with the light and the light leaving the sample is collected, analysed and presented on display as seen here. Raman spectroscopy revealed that the residues on the inside of these skulls contain an unusually high number of certain iron compounds, as seen in the peaks in the spectra, believed to be the result of rapid thermal breakdown of compounds such as haemoglobin in our blood. This points towards the idea that these people's bodily fluids and tissues quickly vaporised upon contact with the pyroclastic flow. The question of how these people died may seem nothing more than morbid curiosity, but remember, modern-day Naples still sits in the shadow of Mount Vesuvius. Every 2,000 years, Mount Vesuvius undergoes a large eruption like the one in 79 AD, but luckily this time around we are a lot more prepared for the next eruption, whenever it may be.